All right, so getting back to our example then, let's just say we have a photon in free space, and it has enough energy, is the energy of the photon, to make two particles. Now, these particles would have to have equal mass, like the positron and the electron, or it could be an antiproton and a regular proton. But the energy of the photon would have to be enough so that by conservation of energy, you could make a particle-antiparticle pair. So that's why it's 2 times the rest energy. That would be the minimum energy of the photon, because you would also need to, if there was more energy left over from that, you'd have to give the particle some kinetic energy too. But just in terms of a minimum energy, this is the condition on conservation of energy. Now, conservation of momentum, if we have a photon coming in with a momentum that's equal to h over lambda, and the positron and the electron shoot out with velocities v, then the momentum of the x momentum of the two particles would have to be mv cosine theta times 2. Okay, because that's the x component of the momentum of the two particles. And theta couldn't be 0, because if it was, then the two particles would instantly just combine back into a photon, right? Because matter and antimatter collide and convert into photons. So the fact that this angle is not 0 is necessary in order to keep these two particles from recombining. Okay, so this is initial x momentum, that's final x momentum. Here is initial energy of the photon. Here's final minimum energy if the particles have essentially not very much velocity associated with them just after the collision. Now let's just take this expression and multiply for the momentum. This is just the sum of the initial momentum let's multiply both sides of the equation through by c. Okay, now if I do that, then I get hc over lambda, which is the same thing as the energy. And so let's just rewrite this then in terms of, okay, instead of v here, what I'm going to write is 2 mc squared, okay, because there's another factor of c here. So I have to write this as v over c cosine theta. Okay, so this is the same thing as that because I've just multiplied numerator and denominator by c. Okay, but we can see now that this expression, which is an expression for the energy, must be less than 2 mc squared, which is the energy. Why? Because v can never be the speed of light, so v over c has to be less than 1, and theta has to be greater than 0. So theta, the cosine of theta can't be 1 either. This expression has to be less than 1 also, or else the particles will recombine and turn back into a photon. So that has to be less than 1, that has to be less than 1. So what we've just proved then is that you can't simultaneously solve the momentum and the energy equations and have them be consistent with each other. And so the conclusion then is that photons in free space cannot produce matter-antimatter pairs. Now, there might be a way, if you had more than one photon, of allowing for this to happen. In other words, if you had a photon coming in this way and another one coming in that way, had them collide, then you could have, say, a positron and an electron taking off in that direction. They could both have the amount of energy total that was equal to the energy of the two photons. And then you could also conserve momentum, because there would be zero initial momentum and zero final momentum. But a single photon by itself cannot convert into matter in free space. However, multiple photons can, like what we've seen here. And also, photons moving through matter can. Why? Well, in this expression here, we see that the momentum is not enough to be consistent with the energy equation for a single photon. But if the photon interacts with matter, then the matter can absorb some of the momentum. And so this can allow then for particle pairs to exist as photons move through matter. So remember that what we're looking for are the ways in which photons can interact with matter. And so photons then moving through matter, if they have a high enough energy, can convert into matter-antimatter particle pairs. And so that is for the highest energy photons. You literally then can get energy turning into matter. And that's just like what happened in the Big Bang. In the first second following the Big Bang, energy was turned into matter. And that's exactly what the Large Hadron Collider does too, is it mimics the energy conditions that happened in the first second following the Big Bang. Okay, so with these ideas in mind then, let's just look at an overall effect that these things can have. This is an observational effect. And realizing too that we haven't looked at every way that photons can interact with matter. We just looked at a couple of the main ones. So in other words, how much, or how many, we could say, photons remain after those photons have interacted with some matter. So you might have a few coming in like this, and then less coming out. So this thickness here then could be some x value. And so we could think of this as being the intensity, I, after it's moved through some substance. So this is the matter that the photons are interacting with. That has a certain attenuation coefficient. And this would be the original intensity of the light. Now remember, intensity is in units of watts per square meter. So we could write then an equation that would have an exponential bound on it. And so I would be I naught times e to the minus mu x, where x is the distance that the photons move through the matter. And mu is what we would call our attenuation coefficient. And so this then would be a function of the material and also of the frequency of the photons that make up the beam. So mu might be different if we're talking about energies on the order of an electron volt, because that would be more photoelectric effect. If it were higher energies like Compton scattering, like a few hundred electron volts, then it would be a different value for the beam. And it would also be a different value if you had such high energies on the order of millions of electron volts that the photons were producing particle-antiparticle pairs. Okay, so for our purposes here, our attenuation coefficient, we'll just think of it as a function of material and frequency. But let's just look at this for a certain value. Let's say that mu is 0.1 per centimeter. Okay, now, how do I know it has units of reciprocal length? Well, because the quantity in the exponential here is going to need to be a unitless quantity. Okay, so that means that if we had this in units of 0.1 per centimeter, then x would have to be in centimeters. Or I could have written mu in terms of the attenuation per meter. Okay, if I did that, then there's 100 centimeters per meter, and so the attenuation would be much larger. It would be something like 10 per meter. Okay, I mean, you could change the units if you want, but let's just say that for this example, we want to find I in terms of I naught. If x is equal to 10 centimeters. Okay, so we could write then that I equal to I naught times e to the minus 0.1 per centimeter times 10 centimeters. That would be 0.1 times 10 is just 1. So that would be I naught times e to the minus 1, or that would be 0.37 I naught. So that means that 37% of the photons make it through. Now if we'd written mu in units of some number per meter, then you could rewrite this then as 100 centimeters per meter. That would give you 10 per meter. And so then you'd have I equals I naught e to the minus 10 per meter times 1/10 of a meter, right? Because 10 centimeters is 1/10 of a meter. So that would still be the same thing, I naught e to the minus 1. So it's independent of which units you use to measure it. And, you know, this is the kind of thing that you could do. You go down 30 feet, say, below the surface of the ocean, and then you have sunlight. And typically something like 10 meters down, you still have a fair amount of plant life existing in the forms of kelp or whatever at the bottom. But you go down 100 feet, which is more like 30 meters, then it's getting pretty dark, and you don't get so much photosynthesis and plant life existing down there because it's an exponentially dropping function for a given value of the frequency and the distance that you travel through the medium. And so things are really dark down there. I once did a scuba dive to 100 feet, and it was dark. It was cold and kind of scary. A lot of pressure down there too. So that's what's happening though. The light is getting attenuated with greater depth. And so that's an example of light traveling through a transparent medium and then interacting. Now, what's causing the interaction? Well, it could be the photoelectric effect, it could be Compton scattering, it could be paraproduction, and there are other kinds of radiation that can be given off as well. Or it could be combinations of all of them, depending on the energy and the intensity of the beam and the properties of the material. Okay. And so that then takes care of the main subjects that I wanted to cover on the, at least for the moment, on the particle properties of electromagnetic waves.